5.4 part 2. We're still doing trig functions to find the unit circle. Our objectives, we're going to identify the domains now. Okay, so now we talked about these. Let's figure out what the domains look like, and we're going to use the unit circle to help with that. And then apply period and properties of trig functions. Okay, so I'm going to give you like an equation. We're going to apply some of these properties to solving that equation. All right. Here we go. So identify the domains of trig functions. I'm going to go ahead, just draw a small little unit circle here as a reference. Okay. Now, looking at a unit circle, let's think about sine first. Okay. Sine goes with what coordinate on the unit circle, x or y? Yeah, y. Okay, it goes with y. Notice, is there any place undefined on the unit circle with the y coordinate? No, right? Nothing at all. Okay, cosine deals with the x coordinate, right? Is there any place in the unit circle where cosine could be undefined? No, there's every value. Okay, so already I know that sine and cosine domain is going to be all real numbers. By the way, I will state that on the board here. We're thinking right now. So sine and cosine, there's not one number I could plug in that doesn't work. Now, let's think about tangent. Okay, tangent deals with the y and x coordinate, right? But y over x. So the only time tangent is undefined is when x is 0, huh? So where's that going to be located? Well, it's not here, because x is 1. So pi over 2, no good. This is fine. 3 pi over 2, no good. So this has some domain restrictions, huh? It's not all real numbers. So for tangent, we don't want, so in terms of, let me put like an angle here. So in terms of theta, and again, I'm going to summarize in a nice table for us. We don't want pi over 2. We don't want 3 pi over 2. Not good. Okay? Now let's think of the other trig functions. We also have what? Secant and cosecant, right? And cotangent. So looking at, let's say secant. Now, secant is 1 over this, right? 1 over cosine. So that's just going to be 1 over cosine of theta. Now, whenever cosine is 0, secant's undefined, right? So let's see. So cosine goes to the x coordinate, so that's fine. That's not good. That's fine, and that's not good. So this already has, so it's kind of similar to this. The domain restrictions, it can't be pi over 2, and you can't have 3 pi over 2, or else secant's undefined. Okay? Are we okay with what I'm doing so far? Just kind of go around the unit circle, just seeing what works, what doesn't work. Okay, and again, I'm going to rewrite this all nice and neat in a table here. I'm just talking things out. Now, let's see, secant. How about cosecant? So cosecant of theta. So that's 1 over sine of theta. So wherever sine's 0, that's no good. So sine goes with the y coordinate. So that's a 0, not good. That's okay. That's not good. That's okay. So at 0, pi, and even 2 pi, right? We can't have. So theta cannot be 0. We can't look at pi, and we can't look at 2 pi, because all of those makes that undefined. And then the last one, cotangent. So it's just the opposite of this. It's 1 over it, which is just x over y. Okay? So it's over the y coordinate 0. Well, we kind of did that with cosecant, right? So it can't be 0, pi, or 2 pi. So one of the things we're going to focus on in this lesson is our domains, okay, and what is legal and not legal when it comes to evaluating these things. And we have the unit circle to help us with that. Okay? So let's go ahead. I'm going to, again, just do a nice little table here. So here's the function, and here's the domain. So let's look at sine. Okay. Domain, all real numbers. If you look on the unit circle, there's not one place on there where it's undefined. Cosine, same thing. Okay, so that's all good. All right, tangent. This is where we have some undefined things. Now, let's think about something for a moment. So it can't be pi over 2, and it can't be 3 pi over 2, okay? So here's what we're gonna write as domain. So our value, my angle, in this case I'm just saying t, or arc, because we said angles, arcs are gonna be the same here. Okay, cannot be pi over 2, or any multiple of pi afterwards. So k is just some integer value, okay? Now, let me flesh that out a little bit. So it can't be this. Now, when is the next time it has an undefined term? Down here, right? And how far did we travel? We traveled a full 180 or pi to get to that point. And then if I travel pi again, undefined again, right? Travel pi, so you keep going on forever. So k is how many times are you adding pi to it to get to your next undefined term for this guy. Does that make sense? Okay. We're gonna do the same thing for the other ones that have that similar pattern to it. Now, your textbook, I'm gonna write this underneath. Your textbook has a different way of writing this. It's not bad. I learned it this way. To me, this makes sense. But this is what they did in the textbook. And again, I'll give it to you just in case if you want to use it, you can. Okay? So what they're saying here is it's excluding odd multiples of pi over 2. Okay? So pi over 2, add another pi over 2, that'd be an even. There's an odd pi over 2, even pi over 2, you're adding, and so forth. So they write it in terms of this. So n is just whatever integer you're looking at here, so 1, 2, 3, and so forth, and that tells you what pi it's not defined as. So either one works. Like I said, I kind of like this one because it's a little bit more easier to read and interpret. Okay, next one. Let's do, well, since we did tangent, we'll do cotangent next. Okay, so look at its domain. So look at cotangent, again, we kind of have not pi and 3 pi over 2, it's the opposite of those ones there. So t cannot be any multiple of pi. Okay? K being an integer. So 1 pi, 2 pi, 3 pi, and so forth. Cotangent is just not defined here. And again, textbook has something a little, actually textbook's very similar to this. We agree on this, except they use n for their integer. I just use k. But either one, so there's your domain. Okay, we got 2 more. So secant. So looking at what I wrote over there, we can see that secant is not good for the pi over 2's. So secant's just going to match this guy, right? So cannot be pi over 2, adding any multiple of pi to it. That's where it's undefined. And just to save space, I could rewrite this underneath here, matching it that it can't be any odd multiples of it. And the last one, cosecant. Okay. And cosecant matches cotangents areas where it's not defined. So t cannot be pi, any multiple of pi. Okay, and again, I could rewrite this underneath here. I'm just saving a little bit of space. I'm not going to write it twice there. So those are our domains for those trig functions. Using the unit circle, we could figure that out. Now that'll be important when we graph these. I like graphing trig functions. They're really cool stuff. So can't wait for you guys to see it. Let's look at an example. So let's evaluate the function. So we're going to do secant of 3 pi over 2. And the other one, we're going to do cosecant of 11 pi over 6. Okay? The first one think about 3 pi over 2 for a moment. What ordered pair goes with 3 pi over 2? This guy, right? 0, -1. So 3 pi over 2 corresponds to the point 0, -1. Okay? Now, I already know that secant is the same thing as 1 over cosine, right? I'm just stating facts right now. So, if cosine goes to the x-coordinate, my x-coordinate is 0, so what do you think this is going to equal to?
Wait. And
So,
that's, oh my gosh.
then 1 over 0, which is undefined.
Yeah.
So therefore, we could say secant of 3 pi over 2 is undefined. Okay? So these 2 steps is just me listing some facts about it. That way I know what to conclude with. So 3 pi over 2 corresponds to this point. Secant's 1 over cosine. We know cosine's with the x-coordinate. With the x-coordinate 0, 1 over 0, undefined. All right, questions?
Yeah.
It's kind of weird having a week off and jumping right back into it. It's a lot being thrown at you. Can't even imagine what's happening in your other classes right now. All right, cosecant of 11 pi over 6. Okay, so let's think about where 11 pi over 6 is going to be. So let me just draw a little unit circle for a moment. Okay, 11 pi over 6. If it was, let's increase it by 1. If it was 12 pi over 6, that's 2 pi, right? Okay. So it's 1 less than that. So we're going to be, what, 4th quadrant? Does that make sense so far? Okay, so we're in the 4th quadrant. And the reference angle for this guy is pi over 6. Okay. So pi over 6, actually we just did it on the first whiteboard. What point goes with it? It's the first one that we have listed there. Okay. So that's going to be, we'll put it here. So 11 pi over 6 corresponds to the point. So it's square root of 3 over 2 and a half. But because we're in the 4th quadrant, that's negative, right? Y-coordinate's going to be negative. So this is the point we're going to be using. Okay, now, cosecant is the same thing as 1 over sine. Okay, so sine's with the y-coordinate, so it's going to be this guy, right? It's going to be negative a half. So let's use it. So cosecant of 11 pi over 6 is equal to 1 over negative a half, which is just negative 2. Okay. Are we okay with me coming with the reference angle of pi over 6? Very easy way to find reference angles. Look at your denominator and ignore the numerator number just for right now. If it was just pi over 6, okay, well that's the reference angle. You're adding how many pi over 6 to get to this quadrant? You're adding 11 of them to get to there. Okay. Questions? All right. Let's keep going. We're going to talk about the period properties of this guy. So that's domains. So one of the things I want us to write down is this. So notice that as we continue to go around the unit circle, our values for all 6 trig functions start repeating. Okay. So in other words, if I'm here at 30 degrees, and if I were to rotate this 360, I'm back to where I started, and I still get the same numbers. It's still going to be square root of 3 over 2, it's still going to be a half. I can add another 360, so that's what, 720 degrees I went. it's still going to be these values, okay? Which is good. So this behavior we call periodic. Okay? So let's write the definition down for it. A function, we'll call f, is periodic if I take my function, I add some value to it, it's the same thing as it was originally before you add it. So for some constant p. The smallest positive value, p, for which f is periodic, is called the period of f. So I'm going to give you a moment to write that down, and then I'll explain that a little bit more fully. For example, so sine of pi over 4 is square root of 2 over 2. Okay? If I were to add 2 pi to the pi over 4, is it going to be square root of 2 over 2? Absolutely. I'm just rotating a full 360. I'm still going to be back at the same spot. So we call that the period of it. Okay, it has a period of 2 pi. Every time you add 2 pi to it, you're going to get back to where you started with the exact same values for it. Okay? So every full rotation of 360 will get to that. Now, that's not true for all functions, unfortunately. So like tangent, for instance, that's not going to be a true statement, okay? Because, well, I erased the picture, darn it. Okay, that's okay. But tangent, I'll put it over here. We know that tangent is not defined for pi over 2 and 3 pi over 2. So its period is going to be just pi. Okay, what's it take to get to that same value that's undefined? It's down here. So it's only going to have a period of pi every time to get to that value. So some of the other ones are going to match that. So let's go ahead and, well, actually, this is perfect. Let's leave that, let's leave it as is there. Change that. So let's put period and property. Okay. Yeah, that's okay. That works out. Or does it? Should I change? There's a reason why I wrote it in that order. I guess I can't keep all of this. Forget it. I'll have to rewrite it. There's a reason why I wrote it in a certain order, so I should probably keep it that way. Okay, so the first one, let's look at sine. So the period for sine is 2 pi, so every 2 pi you get the same value for sine. Property. I'll write it out fully there, okay? So if I take whatever t is and add 2 pi to it, I still get the same value. Cosine, no surprise, it's going to match it. So period's 2 pi. So if I add 2 pi to whatever my angle is, I get cosine of that value still. If you remember from the last lesson, I called them circular functions for a reason, because they're going around, they repeat, they keep going circular with their values. Okay, next, cosecant. Now here's the deal with cosecant. Cosecant goes with cosine, right? It's 1 over cosine. Well, wherever cosine is going to be defined as, cosecant is going to follow there. So it's going to have the same period. So if I add 2 pi to any cosecant value, I'm going to get the same thing as if it was added originally. Secant follows the same pattern as well. secant. I'm sorry, did I say that should? I didn't say cosine was secant, did I? Cosecant? I hope I didn't. Cosecant is sine there. But secant's with cosine, and wherever cosine is, its value is, adding 2 pi to it still gets you the same value as well. There we go. Now, the other two, the ones that I didn't put down, tangent, cotangent, that's where they're not the same every pi. So if you add pi to its value, you get undefined. So their periods are a little bit different there. So I'm going to put these on the bottom. So tangent, it's going to be pi. So tangent of any value, if you add pi to it, you get its same value. And then cotangent is the exact same path. So we're just going to copy that down again. There we go. Okay. And that'll be important when we graph these, which will be the next lesson. Let's try an example. So we're going to use the unit circle and the period of the function to evaluate the expression. So we're going to look at cosine of 7 pi over 3, and we're going to look at cotangent of negative 540 degrees. A lot of tables in this lesson. Okay, first one. So using just all of our knowledge that we got to this point, what is cosine of 7 pi over 3? Now, 7 pi over 3, if it was 6 pi over 3, that's 2 pi. So we already want a full 360, okay? Which is fine. So it's going to be the same no matter what, even if we add 260 to it. So let's take a look. So let's do 7 pi over 3. Let's subtract one of those revolutions. Okay. So we get pi over 3, just to save a little bit of time there. So pi over 3 corresponds to what point over here? Well, half the square root of 3 over 2. And cosine's with the x, so it must be a half. So cosine of 7 pi over 3 is a half. Okay? Now, put it this way. This is saying use the period of the function to figure this out. This is no different than me taking a reference angle. Like, what's the reference angle of this guy? Pi over 3. And then use pi over 3 to figure this out, which is still getting to the same conclusion. This problem just wants you to use the period properties to get there at the same conclusion, okay? So if you're looking at this problem, you're like, well, can't I just use pi over 3, just know that ahead of time without subtracting the period of the function to get to that point? You can. You absolutely can. Okay, let's take a look at cotangent. So cotangent, negative 540. So I'm going in the clockwise direction, okay? It's kind of hard to evaluate functions when they're negative angles, so let's try to use the period property and go the other direction with it, okay? So let's do that. So let's get this to the positive. So negative 540. Now, let's think. 360 is not enough. It'd be what, 2 360s or 720?
Just recall it. Why don't you can we just use pi and then add 540? Since the period for cotangent's pi, couldn't we add 540 since that's what, 3 pi?
3 pi. It is 3 pi. Say it one more time.
Cotangent cotangent's period is
Mhm.
pi, so couldn't we add 3 pi and get 0? Or do we just stick to 360 because that's the circle?
I would. You want to get positive first before you apply the period
Okay.
to it. I would say. Because where that's landing is not 0. It's not landing at 0. It is for the x coordinate, but not for the y coordinate. So we have to be careful with. Well, no, I take that back. The x coordinate's not 0; it'd be the y coordinate. But anyway, let me finish the problem so you can see.
Yeah, okay.
So negative 540 plus 2 of those gets us to 180 degrees. So right there, I'm already on the x-axis. I don't have to use the period property for this per se. So now, this corresponds to the point, well, I erased it again, but I'll put it underneath it. So the 180 corresponds with the negative 1, 0. So cotangent of negative 540, okay? So cotangent is the opposite, right? It's the x over y. Well, x is negative 1, y is 0, that's on the bottom, so therefore it's undefined. Not going to work for us. Okay. All right. Questions on the periods of those? It's not a, like I said, the only two that we have to worry about are these two. They're periods of pi, just because they're undefined, goes every pi radians outward. These guys are always 2 pi, which isn't bad to memorize there. Okay, we have one final thing to do. Let's go back to college algebra real quick. Yeah, let's go back just a little bit.
Yeah.
Just a little bit. So from algebra, and what I'm about to show you is going to be helpful, because when we have like negative angles with trig, it can be a little tricky evaluating. So some of these properties from algebra are going to help with that. So one of the things we talked about was even functions. So that's when if I take negative of an input, it still gives me a positive output. Okay? So remember, that's like symmetric across the y-axis. Okay? And then an odd function, if I plug in a negative input, I get a negative output. Okay? So some examples underneath it. So if you remember, like x squared, I'll draw a little graph underneath it. Okay? If I get a positive x, I get this y value. Negative x, I get the same y value. Okay, so it's symmetric across the y-axis. Odd function, so we have something like x cubed. Okay. So looking at 2 points with an odd function, all I'd have to do is take its values. If I get a negative of that x value, I get the negative y value that corresponds with it. Hopefully it looks a little familiar. It's been a while since we've done even and odd functions. But I can apply this to trig, okay? So let's take a look at it. And I'm not gonna have, I could have space. I don't want to squeeze it underneath there. We'll draw a little unit circle here. Okay. That's a funky unit circle, but we're going with it. Okay. If I were to go in this direction, this is when t is positive. All right, so let's say I travel a certain direction here, and the point that corresponds with, we'll pick 45 degrees. It's easier to start with. So square root 2 over 2 for both of those, okay? But notice, if I go in the negative direction, same distance, we'll do pi over 4, I get square root 2 over 2 and negative square root 2 over 2. Okay, so this is when t is negative. So I'll put negative t here. Okay. Now, one of the things we can look at is sine and cosine. Okay. Let's look at cosine first. So notice that cosine of pi over 4 is square root 2 over 2. Okay. But if I go in the negative direction, cosine of negative pi over 4, well, isn't it still square root 2 over 2? It is, right? So with a negative angle, did my output value change for cosine? It didn't. Okay? That's perfect. So therefore, it must be an even function. Cosine's an even function. So anytime you see a negative, when it comes to cosine, it's the same thing as this positive value. Now sine's a little different. So sine of pi over 4 is square root of 2 over 2. But sine of negative pi over 4, well, what happened to its output? Also got negative, huh? Okay. So negative square root of 2 over 2. So therefore, sine's more of an odd function, right? When it comes to the definition there. So we could do that with the other trig functions as well. But again, we'll see more of this. We'll do some examples. We're going to see a lot of that tomorrow when we start graphing some of these things, where we can swap out a negative with a positive to make it easier to work with. Okay? So let's go ahead and look at tangent. Okay. So tangent, which we know is sine over cosine. Y over x, but we know that sine and cosine do the same thing. Okay? So if I have a negative angle for tangent, okay, what's the output going to look like? Well, let's look at what we just discovered up here. Okay? So we're going to have sine of a negative angle, cosine of the negative angle. Now, if the angle is negative for sine, the output's negative. So this is just going to be, well, negative y, whatever the output is, whatever our y coordinate is. I didn't specify it for this one. Cosine, I know if the angle's negative, it's the same thing as it's positive. So it just comes out to be a positive value for it. So we could see that if the angle's negative for tangent, the output's going to be negative then. So that's more of an odd function there. So we can say here that tangent of negative t is the same thing as negative of tangent. Okay? So I'm going to go ahead, another table. It's way too many tables in this lesson. This is the last table, I promise you. Well, let's make another table with some of these properties in it. Okay? Now the good question is, what board? I guess we'll put on this board. So function, and then we'll put property. Okay. And by the way, I didn't put secant, cosecant stuff, but we can do the exact same thing. Now that we know what sine and cosine are, we can figure out what those are rather quickly. So let's look at sine. Okay. So we know if the angle's negative, the output's going to be negative for sine. Okay, so this guy, I'll put here next to it. That's an odd function. Cosine. So if the angle for cosine's negative, well, the output's still going to be positive. So that's an even function. So far, so good? All right, let's keep going. Tangent. We just did that over there. So if tangent of an angle is negative, well, the output's going to be negative as well. So that's going to be an odd function. And by the way, I mean, do you have to memorize if they're even or odd? No. I'm putting it there as a connection to algebra, okay, as a way for us to figure this out. Secant. So if we have secant of a negative value, we still get its value back. Okay, so that's even. And that one's pretty intuitive, because think about it. Secant's 1 over cosine, so it's going to follow cosine's pattern here. They have the same period. Next, cosecant. So if we have a negative angle for cosecant, we get a negative output. So we know that's an odd function then, if that's the case. And the last one, cotangent. So if cotangent of the angle is negative, the output will also be negative, which is also a characteristic of an odd function. So there's only two evens. It's these guys, secant and cosine. Okay, they're the only ones that are evens, to where if you see a negative angle, it's the same thing as it's positive. The other ones, not so much. But again, that will help us to evaluate and graph, which we're going to see in our last example. So any questions? You guys are doing good? All right, let's apply it. Now the fun part. Use the properties of trig functions to simplify. I got two here, so we're going to do this one and B. Well, I'll put B down here. Secant of negative 2t plus secant of negative 2t plus 2 pi. There we go. All right. So for the first one, I just want to simplify. I'm not solving for anything. I'm just trying to make it a little easier to work with. Okay. Notice that we have a negative angle with sine. So if I look at my properties over here, I know that a negative angle for sine is the same thing as the negative output of it. So underneath here, let's just put a note. So let's just recall that sine of negative angle is the same thing as the negative output of it. Now that I know that, let's substitute it. So this will be 2 times negative sine theta plus 10 sine theta. So we can multiply these together, so it'd be negative 2 sine of theta plus 10 sine of theta. And I think that's what, 8 sines of theta? So if I want to simplify that expression, it's just 8 sine of theta. Now that's a little easier to work with. Like if I had theta to be like, well, pi over 4 is an easy one to work with. Let's just say 11 pi over 6. Plugging into both of these and evaluating doesn't take much time, but it does take time. If I know how to condense it using some of these properties, now that's a little easier to plug a value in and simplify. Okay? Does that make sense? One more. Okay, down here, we have a negative angle, and then we have 2 pi being added to the angle over here. So we're going to use not only those properties, the even and odds, but we're going to use the period properties as well. So we're doing 2 things here. So let's recall that secant of negative of the angle is the same thing as secant of the angle. It follows its path from cosine. Okay. Also, the period of secant of t is 2 pi. So secant of 2t plus 2 pi is the same thing as secant of 2t. Okay. Now, again, do you have to write that down every time you solve it? No, I'm just writing it down so you know how we're getting to the answer. Okay. So now that I know this information, let me just rewrite this. So I'll put it over here. So let me go ahead and substitute. So that secant of negative 2t is just now going to be secant of 2t. Okay. And then over here, because it's periodic, and its period is 2 pi, that's the same thing as, well, secant of 2t. So there's there's 2 things happening here. The negative 2t is still going to be positive 2t, because we know of that property. And because it's periodic, even adding 2 pi as well, is still going to give me the same result. So at the very end of the day, this is equal to 2 secant of 2t. And again, that's easier to work with than two separate values for. So using some of these properties can really help us out. Okay. Any questions on domains and periodic properties? Anything like that? Think we're good? All right, you guys are awesome. I have